Hello, this is Katana, a utility AI for football. And what are we going to talk about today? The main goal, like the goal that we want to score, like what is it? What was the intent behind this project? The field dynamics, all the different elements on the field, like the ball, the players, and the goalposts, and how these different elements interact with each other. What are utility functions? And utility AI, the name speaks for itself. Utility functions are the brains that power this utility AI. And finally, how do we take all of these concepts and put it all together? So, utility AI is really powerful in helping us prioritize different actions. If you have a set of different actions like kick, defend, dribble, and attack that you would like to choose from, uh, if you had to do it via behavior trees, it would be a kind of arduous, right? So utility AIs help you sort of prioritize which action to take at any given instant of time. And using a utility AI in a football game just hits the sweet spot. So what I hope to achieve with this project is demonstrate how a utility AI can be used in a football game and how it is quite simple and elegant, although it's pretty powerful. We know how traditional behavior trees work. And the key differentiator between these two, the utility and the behavior trees, is that behavior trees are pretty hard baked in, right? If you use them, you would many times end up with situations where you would have a if then else sort of ladder, like if this value is zero point 0.3, then go down this branch, else if it's zero point 0.7, go down this branch. What utility AI helps you do is helps you avoid the sort of if else then branches, and then helps you dynamically score which nodes are most relevant at a particular point of time, given the different constraints and the sort of utility functions that are being defined. And we pick the ones which score the maximum amount of these. It's usually the maximum, but you can also define different utility selectors, which would choose maybe the minimum or like a random above a certain threshold. And what are the different field dynamics, like when you talk about football? Of course, when you talk about football, like you would think about the like actual game and like maybe FIFA, like the 3D environment. But in order to create an AI and demonstrate how utility functions work, how a utility AI works, you don't really need a sophisticated 3D environment. You can do it in a really simple toy example and showcase its behavior as well. When you talk about football, there are a couple of key different indicators or like parameters that can be used for a utility functions. And one thing I would like to reiterate and emphasize on is that football, when you're trying to simulate it in a game or on a computer, is all about vectors, vectors, and vectors. So some of the other indicators that you can use are like ball progression, distance to your team goal, opponent team goal, what's your current velocity, what's the kick force that you're going to have, and of course you need a goal scoring mechanic to figure out if your AI is actually doing its job. And what are the different utility functions, right? So in the setup that I've created, the each player can basically express itself in four different intents or intentions. For the Katana AI, the player has like four different intents, which are basically attack, defend, dribble, and kick. Now let's take a look at how these curves actually look like. And I will also explain what each one of them means. So the attack intent basically says how far away you are from the ball, and it makes you chase the ball, like makes you push towards the opponent's goal. And what the defend behavior does is it gives you a predefined sort of radius around your own goal. And if the ball enters within your sort of detector zone for your defense behavior, then you would start upping your intent to become defensive. And dribble is basically, think of it when a football player is playing a match, he would at many times need to intercept the ball, which would have a different velocity and direction than his own. So he would need to course correct and match the angle so that he is in line with the ball and also in line with the opponent's goal. So that's dribble, and kick is the intent that the player expresses. Like when he's closer to the ball, he has a willingness to kick, and as you're getting closer to your opponent's part of the to the opponent's half of the field, your intent to kick should likely go up because you want to score goals, right? And finally, how do we put all of these different concepts together? We know what's a behavior tree, we know what are utility functions, and uh, the magic behind them is the scoring functions that we have, which is like the score attack, score defense, score dribble, and score kick. So we write a score for each of the different actions that we have, and there's something missing. And the something is the secret sauce. The secret sauce is basically this. It's as simple as this. You take a normal behavior tree and then you shove in this node just below a sequencer node. So you have a sequencer node, you shove in this node called a scorer. The scorer determines the best scoring node amongst the nodes that are further down below it. And it denotes the best one with a certain task ID and it stores it. Any node that matches the task ID executes its internal actions, but all of them will return the status of running true because that's how a sequencer node works. Uh, Only if all its children nodes are returned successfully is the sequence node successful. And now it's demo time. Before we dive into the actual game demo, I would, however, like to give you an intuition of how the different utility functions work and how do they respond to the different parameters, right? So I've created a simple demo on Desmos. So let's take a look at that. Just a second. Okay, so this is the attack utility curve, and as your distance to the ball increases, it's normalized from 0 to 1, your intent to pursue the ball or attack towards the ball increases. But as you get closer and closer to the ball, your attack intent drops down. And this is pretty realistic behavior if you watch a couple of football matches. The next behavior is the defend intent. And what this basically says is that if I am closer to the defense radius of the goalie, then my the goalie's intent to start defending should go up. This is, of course, I'm talking about the ball. So if the ball gets closer and closer and closer to the goalie's defend radius, then the intent to attack should go up. And it's not linear. It's not linear because as it's closer to the goalie travels around a lot or like is on his toes, and they have faster reaction times as the ball gets closer. So this models that behavior. The other action is the dribble behavior. This is sort of like the course correct. Remember the one that I told you where the player needs to align himself with or herself with the ball and the opponent goal in front of them in a straight line. So this basically corrects for your angle from your current velocity to the desired velocity that you want to go to. So it's modeled pretty well with just a basic straight line, and it's normalized with respect to pi. The next is the kick intent. It's kind of similar to the defensive intent, although not really, because this one is more steep. Because if you are further away from the ball, then you can't really kick, so your kick intent is pretty low. As you go closer and closer to the ball, your kick intent should rise up. And also note, uh, you can tweak this knob for ball possession, so ball progression. So at any given point of time, if you are further along and closer to your opponent's goal, you should be more likely to kick. Your intent to kick should be much higher. So this reflects that the way the curve turns. And this is also the aggression behavior. The aggressiveness behavior kind of tries to cap how high your final kick force can go. So if a player is more aggressive, of course, his kick force for a given distance and ball progression will be higher. And if it's lower, it's going to be lower. So yeah. And now take a look at the football 2D simulation. Okay, so let me take a look at the different players, disable these guys. Actually, maybe enable the attacker because you want to see some interesting behavior and set play. So what is now going to happen is each of the players have the four actions that they can perform, and those are their four different intents: attack, defend, dribble, and kick. And it picks the maximum at any given point of time, and those knobs are like twiddling up and down, as you can see. So the player starts off and he is heading towards the goal, keeps pushing. When he kicks the ball, it's further away, and then he needs to go and chase the ball again. So this is simple, and it's not very interesting if you don't have opponents in football, right? So let's go ahead and add a couple of opponents. Yeah, so let's take a look at this. Both of them try to chase the ball, and now red is trying to score. Red scores, and you can see over here on the right side, there are these different knobs that we have. For example, what's the maximum kick force a player can have? What are its values for the kick action, the dribble, the defend, and the attack action? It of course picks whichever is the maximum among those. And so right now you can see that red is really dominating because over here the red player has an aggression value of 0.7 and a kick force which is kind of high. So if I was to reduce this kick force to maybe 2 or something, and also reduce his aggression to maybe 0.1, the red player would not be that aggressive anymore. And what you are now going to notice is that the blue player is going to keep pushing, and then now I think in about a second he's going to score a goal. So there you have it. So you can tweak all these different knobs and you get to see a pretty realistic simulation. And if you're wondering what are those wonky sort of diagonal lines, those are lines to prevent the players from getting into a corner and getting stuck. So yeah, let's go back. Stop this. And that is it for the demo. And yeah, this was fun. Uh, cool. See you guys. Thank you.